Hello, everybody. First of all, I want to thank Shantanu for the invitation to be here. I'm always eager to talk about this kind of stuff with young scientists and like their ideas, and I like this. Personally, my scientific work focuses mostly in quantum cryptography and particularly in oblivious transfer and protocols beyond quantum key distribution. This is a project that we did, I didn't put here the author, sorry, I forgot, but it's a team in Lisbon with Paulo Mateus, Ricardo Paleiro, Nicola Pankovic, and Andres Souto. We together, like one day, we got together and decided, like, what if, right? And then we started developing the idea until we finished with this paper, which is, I got published last year. And I think I am eager to show this thing because it's something that I don't often have the opportunity to talk about. Okay, so first,
is it on email to click on the site? No, yeah.
Click it.
Try clicking.
Yeah.
Send.
No? Oh, okay.
With the saying, you can see the audience. Somebody else.
First of all, I want to ask you how familiar are you with the concept of Turing machines and the idea of Kolmogorov complexity, classical Kolmogorov complex? Has anybody of you heard about it or studied it or maybe like have any sort of contact with it? Yeah? Okay.
The Turing machine, yes, I don't know.
Yeah, the Turing machine is more universal, but Kolmogorov is something a little bit more of an issue. Okay, so then I'm going to explain a little bit the idea. So first, we're going to discuss what is the deal with classical Kolmogorov complexity, what is it used for, and maybe what would be the intention into generalize it for quantum systems. Then we're going to discuss the machine model, right, which we call deterministic-control quantum Turing machines. Then we're going to define what Kolmogorov complexity is for quantum states within this machine model. Finally, then we are going to discuss two applications of the quantum. This one is related to study the limits of quantum state cloning from the point of view of algorithmic complexity. And then we're going to study the quantification of the complexity of correlations in quantum systems using this programs. So I hope you like it, and I very much encourage you to ask me questions, raise your hand in any moment you have any question. Because for me the most important is that you can take something away from, right? If I start saying stuff and then you say yeah, and then you leave, then maybe it will not have, it could have been spent better the time. So first of all, I'm going to use Shantanu here to do a small exercise. Right? So Shantanu today is going to be Mr. Kolmogorov, and I'm going to be his system. And we have this set of box. And so the idea is that Mr. Kolmogorov owns a hotel, and it's a each pitfall. There's two different rooms in the hotel. So I am working here, and he's managing from some place. I don't know. And he will call me every morning and will tell me, "Hey, please turn on the lights and room that." Right? So right now, all the bulbs are off. So first, I will ask Mr. Kolmogorov, what should I do? And I want you to explain me over the phone what should I do to achieve this configuration.
From the starting configuration?
Yeah, it starts like this. This is how it is right now, and you want this to happen. But so how do you tell me what to do?
Turn on the first row and then turn on the second.
Yeah. Imagine that this is not necessarily a row. This is just a set that is not necessarily okay. So turn on the first row, the second row. So fine. In general, we can say turn all of them. All right. So turn all the. So this was, if you think about it like this, it didn't cost him a lot. He just turned on the bolts, and then I am the one who has to go 1, 2, 3, 4, 5. And so this embodies the idea of it's easier said than done. Like I think the Kolmogorov complexity. So now, Mr. Kolmogorov, what do I do?
Even or turn on
the even positions, right? Okay, very good. So turn on every even position. So it's almost like now I have half of the work. But for him, it was basically the same. It's a bit more longer. His explanation was a little bit longer, but it's still very good. Like it's still much more work than it was.
Doesn't it depend on your shared agreement of For example, if you have shared communication.
There should be some sort of understanding of how I understand what he says. Right? So, for example, he might give me a booklet saying, when I say this, interpret it in this way, right? So this, of course, like we assume right now, just for the purpose of the experiment, that we are using natural language, but eventually we'll discuss this in the context. And now, what about this in second order? What do I look at?
It's hard.
It's kind of okay. So turn the first two, then skip the next, maybe then the third first three, and then skip the. So now it's start becoming harder for him. But if you see, this is more or less as hard for me as the previous one, but it's harder for him. So what's happened, right? So there is this notion that there are some structures that are difficult to explain, difficult to describe, right? And how we quantify the difficulty of describing something is through programming, like it's to how long is a program in which I have to get the computer to do the task. So in formal Kolmogorov complexity, Mr. Kolmogorov will be the program, and I will be the computer, the machine running the program. So, but as Atul mentioned, right, what if we have some sort of understanding previous? It doesn't necessarily always have to say this in this way. There are many ways. Actually, when I randomly selected this, and I went to the encyclopedia, the big encyclopedia of mathematical sequences, to see integer sequences, to see if this was there, and it's not even there. Right? So you may even find it. You know, I said, okay, Mariano, look at the encyclopedia and grab A1223. And then I will say, okay, so I will look at the encyclopedia. Or we can just say, look, Mariano, boom. And then I will know. But if we have a previous understanding of what this means, right? So whenever there's a one, so what is Kolmogorov complexity? Like, it's a mathematical formulation of the intuitive idea of how much information does an individual object have. So I don't know if any modeling, and you have, for example, some data, and we wanted to create a model to describe the data. Right? So one way you can do it is like, I guess you are familiar with the concept of overfitting, right? So I have a lot of data, and I describe a model that exactly describes all the data. It's probably not going to be a very good model, right? Because it's grabbing noise, right? So you have this Occam razor approach in which saying, the simplest model that describes the data, maybe not perfectly, but very good. Maybe that is, but how do you say how simple is a model? Right? So you can use Kolmogorov complexity to study how simple is the model, and then you can do some sort of scoring, saying, well, the model produces my data, and this is how complex it is. And I will do some sort of trade-off, for example. So we also have a study of randomness or stochastic problem.
So just to make sure I'm following the formalization. So in the example with the light bulbs, you have a program that will output which light bulb is on or off as binary.
Basically, the program will input both of the string. So the bulb will be zeros and ones, right? That will be kind of binary.
This is the string that you. Then how do is there any input to the device, the distribution?
So in that case, but because Turing machines, you can grab like an input and then grab the program that the machine that doesn't take the input, right? But so in this case, you can think about a machine that just runs. You don't put any input, the machine just runs.
It's and like any model outputs, yeah? Like an any model.
Yeah, like this exactly.
Every length is supposed to be the any model. That's just a problem. Otherwise,
all right, yes.
Turing machine generates change everything.
So I will discuss that in a moment. So let's pause that, and then I will come back to the answer to the question. It's a good question, but it's actually a very important question. So I just want to talk about now the the context, and then we will do talk about it more specific. So the study of randomness. So similar to the example of the bulbs. So you know that, for example, the bulb has all even turned on, and the last bulb, if you consider them like coming from some random distribution, except for a uniform distribution, both of them have the same probability of occurrence. But there is some notion that this one, I'm going to just come up with, this one is more random than this. This one somehow has some structure, and that makes you think, this is not a random thing. But if I randomly sample something, it will give me something that kind of looks like this, right? It's unstructured in some way. So there is a way of quantifying the randomness of a sequence through Kolmogorov complexity. If it is very difficult to describe, it's more random. And then there is this idea, there's this theorem called the Grudnow theorem that actually connects information theory, normal information theory, with algorithmic information theory. So it compares, it's a beautiful theorem that relates Kolmogorov complexity with it. So it's you can use to study randomness.
But how do you make sense of the dumb fact that every specific sequence is going to be just run like a difference?
Exactly. So this is how it's what is it. So what you know is that if you sample, for example, uniformly from a set of 20 strings, most of them are going to be very happy to spend. And as you become longer and longer, as n becomes bigger and bigger and bigger, it becomes overwhelmingly probable that a string from overall complexity of the whatever you sample, the output sample, it will be maximum. So there's a file with the second configuration of bolts. That file can be very short, but the third configuration, the file will be a little bit bigger, right? So how much can you compress a given like set like string of bits? It's also part of the application. And now we can ask the question, okay, so now that we have this notion, how can we meaningfully apply this to quantum systems? And what meaningfully, I really like, it's a bit of also some sort of subjective, like I want to understand, to either have this for applications in some sort of like modeling or cryptography, or at least I want this to be used for me to understand a little bit better quantum mechanics, to get a bit more insight of quantum physics. Maybe can I use it for that? And this is as a basic scientist, like I like the idea of seeing this and saying, looking at theorem and saying, okay, this theorem makes me understand better quantum mechanics, quantum physics. I like this idea, and this is what we were trying to aspire to when we were. So we'll begin with the definition of Kolmogorov complexity. So here is your person is going to. So, all right. So what is classical Kolmogorov? So let x and y be two strings. So these are strings of any size. So it might be from the zero size string to whichever. Right? It belongs to the set of binary strings, and that you be a classical universal Turing machine. Like I suppose you all understand more or less what is that, right? So the algorithmic complexity, usually we call it Kolmogorov complexity, but I would call it algorithmic complexity. It's the same thing. Of x given y is given and default. So you have x given y, and this is the infimum of these p's, which are natural numbers. And then you have here the size p. This like modulo means the number of bits of that string. And then you have of the number, right? If the number is 80, this will be the number of bits that you need to represent the number 8. But that will be specific. So log 2 and so such that when you run the universal machine with the input p, so you have, in this case, you have an input that is a tuple, a order pair. It has two numbers, right? P and y. Then as an output, I get x. So P, so U is the universal machine, nothing, but so P will be understood as the program that U is running, and Y will be understood as the input of the program. So normally, machines, this is a universal machine. Normally, Turing machines can be enumerated. Typically, for example, if you make a set of all Turing machines, there are a theorem that says that there exists an enumeration of which you can say the first one, the second one, the third one. So you can sometimes understand the program as the index of such enumeration, right? So you're running the pth machine on the enumeration, right? Instead of saying U on P, you instead run the machine P, the pth machine on input Y. This is another way of understanding. I don't know if that somehow is related to the question you were asking.
So your definition is that the system of the quantifiers, right? You want to say that U is fixed, and then for all X and Y, it has to be fixed, right?
Mm-hmm. Well, it's a quantity defined in terms of X and Y, but so
but U is fixed.
U is fixed. U is fixed.
Yeah.
With a fixed U, the complexity of this pair is given like that. So now I have an infimum there, but the set of P's is a enumerable. It's a discrete. Why would I use an infimum? Why would somebody can answer that question? It's intuitive. Why don't they use the minimum? Usually you use minimums in continuous set, right? But why would I use a second? And those go round. I'm sorry,
Number of bits you want to
I'm sorry, I cannot.
number of bits that you want to reduce.
Yeah, number of bits. But what I'm asking is like usually because it's a number of bits, it's a natural number. Why wouldn't I use a minimum? Why do I use the infimum?
Maybe that will come down.
Because I want for this to be eventually applicable for uncomputable objects. So when a number is uncomputable, there is no problem. By a vacuity argument, the complexity will become infinite. So it's well defined for any object. Okay. All right. So well, just some notation. We'll denote the empty string as this square because I don't have anything left.
So in the bulk example, P is like the program that reads the qubits, and Y is the specific instance.
Yeah, imagine that the Turing machine is this laptop, and then you have several applications. So then you choose the P application, run it, and it will ask you, hey, what is the input to this? And you put Y. And then it will run and it will give you X. And then that will be kind of like the idea if you relate it with
What in the bulk example, Y is Y next.
Why are you such a saying things?
In the bulk example.
Y will be okay. That's
like turn on all the bulbs.
So in that example, because there was no given,
that's what it was.
So that will be just K of X, which you don't have IY, and then you just run the machine and it will import. Okay, the Y is like the empty string. What would be the empty string? So for example, Y will be something for us, me saying, hey, I have something, I can, for example, look, Shantanov, I have this configuration up until here, right? So what do you want? And you can look what I have and say, okay, just turn off the last one. And then it will be easier because I already have most of this done, right? But of course, like maybe I have some configuration in which, for example, let's say this, right?
Yeah, you're saying given
like how easy is to construct this from here? That's another question. There is a concept here that doesn't have a machine. And maybe this is a shortcoming of me while writing this definition. This should have a dependence on you. This should have a dependence here on you, right? But it usually doesn't because there are programs that translate one machine into another. You have two universal machines, perfect. You have two universal Turing machines. There is a translator program, another machine that will translate programs of one. So the enumeration of programs in one into the enumeration of the other. So that speaks length for each pair of machines. So because like the translator is a fixed length machine. It's the translate. It's the whatever machine does the translation. So that means that the Kolmogorov complexity between, like the difference between Kolmogorov complexity of two with different use will always be O1, like some sort of fixed. So what we usually treat it is as something that depends on n. How much the complexity of this type of pattern, so this family of patterns, depends as the string size grows, and this will typically depend on n. So it's always plus O1, and this O1 we ignore. This is very important. I will mention it, but it's very important.
So n is the length of y or x? Y row.
N will be kind of like the length x. In our example, it will be, for example, his n will be 20, and you can like try to generalize it. So you will try to, you will not specifically talk about the Kolmogorov complexity of this with n equal 20 because it's a bit meaningless because of this reason. But you can just change the margin, and it will be the first, and the other will be the million, right? So you will want to see how it grows with n, and then you will see the pattern of growth plus O1. Right?
So it's x, right? That's what we care about. Like the n,
X or y, I wasn't sure.
that's the length of x.
X. Y is the side information, like the advice for some people like advice. Well, no, I wrote it. Case machine independent plugin. And then this is what I'm.
That's one thing. It's a very using to use a translator. But the issue is that would involve two programs. It's not like a single program.
So you have one program in one machine, one program in the second, and a third program which translates from one to the other. So the O1 is the length of the program that translates from one into the other.
So it's saying,
so if the program actually works, the one that translates all the programs here in the programs of here, it's length independent of what you're doing.
so but to get specific configuration, I should give the initial program and the translator.
No, you just need give the initial program and the translator.
So the translator is
The translator is fixed between two machines.
okay.
And the translator is the O1. Is the O1 that you opt for. Okay, so now we will just talk about a little bit quickly about encoding tokens, because it will be useful when we try to describe quantum systems. They are described usually with variance density operators, which are these complex numbers. So we want to understand how those things relate to bits, to bit strings, right? So very quickly, right? So a couple of strings, like a ordered sequence of strings, can be encoded into one single one by using, for example, a technique of this, in which what you will write is like you have x1, which has some amount of bits, right? So what you will do is write a number of ones equal to the number of bits of x1, and then you put a 0, and then the idea, the decoder of this will be such that you will count number of ones, and whenever it finds a 0, it will, let's say there are 8, right? So it will 8 ones, you will see a 0, and then it knows that the next 8 bits are the first 3. Then it starts again counting ones, and you see a 0, and then you know that. So this is a single bit string that can be used to represent a token. The reason I'm talking about this is because doing this makes the string longer, as if it would just concatenate all of it, because you're adding these things, right? You're adding these lengths to the 0. So, so here I'm saying that this L, it's the string of ones, the length of this, and each component will add a number of bits equal to 2 times the length of your component plus 1 to the encoding string, except the last one, which doesn't need anything. Like once you know, the last one will not need it because it doesn't need to tell you the next one. But, so it works like this. Just to say that encoding a token is a little bit more difficult than encoding a big string, because you just have to specify the cutting point.
This needs to be done like L of x when it's L yes.
You can define recursive way of this, and you will find that these are very optimal. So the recursive program will also be optimal in terms of like the overhead that you pay by putting there.
So I have one question. So x1 and L of x2, right? There's no delimiter between the two. Right?
No, because you know how many bits x1 has.
All right.
So you know that after this, I am already reading the length of the next. So for the last one, I don't need to give this because I just finished. Something anything. So natural numbers can be encoded in binary string, for example, as I was saying, in other contexts, but for example, with the lexicographic model. So that means that, for example, the 0 will be 0, the 1 will be 1, but then the 0, 0 will be 2, the 1, 0 will be 3. So it's not quite binary representation of the number, but it's like, for example, a bunch of zeros will be a 0 if you just took it as binary, but a bunch of zeros will be some number, even let's see what happens.
Yeah, I was just going to ask why you can use binary to write the length of the string, because like, wouldn't that be shorter? That would be like,
because you don't know when to stop reading. Like, for example, you want to encode like this 8. So say I'm going to write the 8 in binary, right? But when do you know when you finish saying the number 8, right? So that's the problem.
is this the shortest problem?
This is a problem. This is a
And if you add an extra character, of course, everything is confusing.
exactly.
Is it why do I thought it's okay to add one or two characters?
Yeah, it's okay. Like you can do it whichever, and in the end, it will change a little bit the complexities, but not in a way that, like for example, you can make a. The problem is that, for example, okay, like if you add an extra, this is a specific way in which you use the extra character, which I'm gonna use it. I'm gonna like cheat a little bit to facilitate things, but for example, if you have an extra character, and I add the number 2, right? And you will say, I will use the number 2 somehow to encode the things, right? Then you also will want to have strings that have 2 inside. Right? You don't want to necessarily use the number 2 only for the limiting, because then you are also, whatever you're gaining here, you're losing it somewhere else. You're not taking full advantage of your apparatus, right? Yes, and then rational numbers, you can, and vectors of rational numbers can be encoded as tuples of naturals. So you can put like denominator sign. And so as long as you have a good encoding, you can just put a bunch of natural numbers, right? A bunch of bit strings, which can be reinterpreted as natural numbers, numerator, and then you can do whatever you want with natural numbers. Beautiful, right? Now, what happens with real numbers, right? So what is a computable number? A real number is said to be computable if there exists a Turing machine which on any input in the naturals will output this rational number, which is somehow encoded, right? So we can talk about it, such that the distance between the real number, my target number, and the whatever I'm outputting decreases with k. So you will say now the input of the program is interpreted as how well the approximation you want it to be. You can define this to be different. You can define this to be 2 to the minus k. All of them lead to the same results and the end of it. So that is a computable number. Are we clear on this? Important definition.
Why do they specifically 1 by k?
That's what I'm saying. You can use anything that converges. Yeah, anything that converges is okay. But I don't know if there are some things that converge too slowly that may break something. So I will not want to say any convergence works, but at least this one gives you the same as if you use 2 to the minus k, for example. No, you don't get anything. Obviously, complexities, time complexities change drastically. But algorithmic complexities.
Oh, do you think there's a theorem that says regardless what function you use over there?
Maybe, but I'm not. I'm not very aware of it. Maybe it will be. Yeah, it's a good question.
Because simply, it just increase the time probably.
Exactly. It makes sense to me that it doesn't matter. But it doesn't matter. Like if I look at all the proofs, I think I can just do with anything that
Question.
Yes.
Storing the rational number.
Sorry?
How like storing the rational number?
The rational number in a tuple. Not tuple, but like I explained.
So is it just some ratio? Or?
It is like, for example, you choose a tuple of 3. One is for one is the sign, and the other is the numerator, and the other is the denominator. And then you have it. But there are other better ways. So then you have complexity of a number. Right? So we define complexity of a string, but now the complexity of a number. Right? So let R be a real number and U a universal Turing machine. The Kolmogorov complexity of R is given by, so now it's the infimum of all the programs that compute R. So remember, below R, before I demand that my program outputs the string that I'm looking, and now it doesn't output it probably ever in general. It just approximated as you put an input, it will give you something that is closer and closer and closer to the number. And how we encode natural numbers, real numbers, in those programs. So if I want to say pi, how do I put pi in a computer? Normally, and this is the reason I'm talking about this, because normally we will put some floating number variable that it's close to, right? And then we will work with that and do our calculation. In this case, we know. In this case, we will, instead of putting that, we will put a program, right? A function, maybe you define a function upstairs, and then you put a function that computes pi in this sense, right? And that's fine. So it's exactly that sense.
Are there examples of numbers that are not?
Usually the numbers that are not computable are related with some sort of like a statement regarding the halting problem. For example, like the Chaitin constant that tells you what's the probability that a random program halts. It's somewhere between like 2.8 and 3, but nobody knows how much is really like the. So nobody can approximate it to them. All right, and now we define the machine model. How much time have I? Maybe I should start going faster.
How to know?
We still have it. Okay, so we'll define the deterministic control quantum Turing machine. So a deterministic control quantum Turing machine is defined by the following pair. So this Q is a set of states. So I call it Q1, like Q started, Q2, Q3 until Q halting. Then, and delta is a function we call the transition function, where Q and R are respectively a finite set of control states containing at least two distinct states, the starting and the halting. It must have one state that when it reaches it, this machine stops. And the transition function of the computation. Now this transition function, but things change. So what will the machine do? It will look at the machine. Usually you will see it as having like a needle, and you will have how do you call this? Tape, yes, a tape with symbols. So it will look at it, and it will look at the symbol it has in front. Okay, and it will look at what state am I? All right, and then so this is the thing. And now it will do the following. It will select a unitary operation from a universal set of unitaries in the Hilbert space. Well, you can choose whichever Hilbert space. There's qubit Hilbert space. So the tensor products of qubits. Okay. Then it will yes. Then it will. Let's ignore this part for the moment. Right? So it will choose a unitary, right? It will choose some symbol to write on the tape, and then it will choose to move the tape either left or right. So this is basically, this machine has two tapes, a classical tape and a quantum tape. So what it will do is look at what is written in the classical tapes. With that, and to get the information on which state it is, it will do something in this classical tape and then move. And it will do something in this quantum, then it will apply some operation in the quantum state and then move the element to the left. So this is what this is doing. That's in short. In this case, we're using qubit spaces, but in principle, these are infinite. There's a Hilbert space that is composed of infinite, some sort of infinite tensor product of qubit space. So how does this look? Right. So this is what we will interpret as the input of the machine. So you have, I'm using for purposes of easiness of explaining, I'm using this block thing. So I have the classical input. Then after I see my first block, I interpret this as the quantum input specification, which what it gives me is which this will define my input Hilbert space. It's a S-bit Hilbert space. So I will go to what I call the anchor set, which is the reference set for quantum system. And from there to the right, the next N S N, which is constructed from S. So this is a number, right, which has S bits, which denotes N. And the next N space qubits will be my quantum units. This is the idea. And what we'll do is that start moving, no? Move here, look what I have here, you look at my state, and now change something here and move here, and then go here to apply some operation, and then move here. This is what it will do, and then we track until it reaches the halting state, and then it will have something that looks like this, right? Something to the right of the origin tape cell. This will be the classical output, and then it will tell you which is the quantum output. So this is M will be the specification on where my quantum output is. So this is allowing me to only through unitary reversible operations, like it will allow me to output density, general density operators, because I can create like some sort of big entangled states, and a measurement can be modeled as you entangle with the measurement apparatus and then just trace measurement apparatus. So that will be the idea here, right? So this in general is a pure state, but when you output it, you output only part of it, so you can output whatever arbitrary quantum set. So that's the idea of the deterministic control. So what are big?
What is the global approach? Like what are their properties? Like are they on basis?
What is what?
Something the flow one, flow two, on the date, like on the
input states.
The input states.
Then the previous time.
So this.
Yeah. So for example, let's say like I want to do some computation on some given unknown state flow. Like how would that like translate into like this picture?
So what we'll do is like you will read this, and upon reading this and also reading this, the machine as a classical machine, and this is why this is called deterministic control. So this machine is semi-classical in the following step, right? It will only look at this. It can only really react to what's written here. It can never do anything regarding what's written. So what's happening, it cannot look at this and decide to do anything about it. It can only look at this, say, okay, this is telling me to first apply a C naught here and between this and this. And then I will apply some one unitary here and move here. And then I will do some swapping between this and this. And then I will come blah, 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 blah. And you will start constructing like some quantum state here and in the form of some in the form of big unitary that is the result of applying all the small unitaries in each step of the machine. So at the end, the machine, what it does is applies an operation here, but it never knows or needs to know what's here. It never reads this. I don't know if that was your question, or maybe I'm answering something.
The point was, do I need to specify the size, the dimension of the one or two?
You have to. That's the quantum input specification.
And is there any sort of restriction on
No.
Whether they are separable and entangled?
No, nothing. It just you already are specifying here the Hilbert space that is considered to be the input. And this is just for correctness of computation.
So the way I understand is that the x1, x specifies which unitary is to apply.
And whatever other things you want to do in the classical tape. Right?
And the n1 to ns specifies which ones to apply the unitary to.
Not quite. You could imagine this not existing. This not existing, but you run into problems that then the quantum input is not one. Because this state can be in any arbitrary initial thing, right? So you have to define what a quantum input is. So somehow there has to be some specification of what quantum input is, so you can define what computation means. It's just for that. In reality, it's just a well-definedness feature. But in principle, you just do things, right? You just don't really need to know what was the input to begin with, right? It's just you need to introduce the information somewhere or something break. That's the reason this is using.
How does it differ from uniform circuit? Basically, it's just describing a circuit, right? That's pretty fun.
So uniform circuits. So this is stronger. You don't have to be uniform. This is anything. So you can
but you are uniform because you're making a Turing machine that you state the description of the circuit you would apply, right? Not one to one. So it is uniform.
So, but the uniformness of the circuit has something to do with the size of its description.
Yeah, sure.
So one may have to be uniform in principle, right? It is because it's just it's not necessarily.
Okay, my uniform was more of the fact that you can produce it from a Turing machine, but you're saying it has to.
No. If you say uniform is a statement also of how the size of the description of the circuit grows with the parameter or thing. Right? So, for example, you have maybe the operation that swaps inverts the you have a string and it will invert like flip its right? So in principle, if it was like a quantum circuit, you have to state swap here, and if you put an extra bit, then it will be a different circuit because the original circuit only applied to n. If you want to implement one, you need a new circuit that also includes the extra bit. Right? So the size of those circuits can grow as the n grows. And the uniformity what it tells you this can be done efficiently. This description grows somewhat polynomially with the.
But you don't think there are also uniform exponential circuits?
I'm not entirely sure right now, but I believe that
because it's just poly slash so whatever p slash poly, so it will also be x slash poly.
So what I'm not remembering now is exactly what is the condition for result of a uniform. It's not, but I know that uniform comes with the condition. If you don't say uniform, you refer to any circuit which description may be arbitrary, no statement about that, and this doesn't put any restriction. Very simple.
It is that the Turing machine has to produce it.
Exactly. The Turing machine has to produce it, and then you could like maybe compile the Turing machine into a circuit. And then
For instance, not in circuits that's all one. Well, you're non-uniform circuits. So yours is still uniform in that sense.
Yeah. Yeah.
Anyway, we can discuss it now.
Yeah. Okay. That's it.
In stage, you only account the classical thing, or is it like quantum and classical?
No, this is on purely classical. This has three symbols: 0, 1, and the block. Only these three can apply. And this one can be any arbitrary quantum with state.
But when you're talking about the states and the cycle, all the states they set. As you talk about only classical data.
You mean so I'm not understanding very well.
No, if you go to the formal description for the transition function, then you have Q cross A. So it's talking about Q. This Q contains.
Q is the set of quantum operations. It tells you Q is the quantum states of the machine, not quantum of the states of the machine. So maybe the Q is confusing because normally in Turing machine terminology that's Q, but then Q now it's quantum, so it's not confusing. So Q in this sense is not in quantum; it's just the set of states of the machine. So I can be in state 1, 2, 3, 4, 5 until halving, and these are classical states. The classical thing.
How do you decide if it is last halting step or not? You can't really do quantum state.
No, because these are classical. So you can know what state you are in. This is a classical thing. So this machine doesn't ever, the behavior of the machine doesn't depend at all on what's the content of the quantum. It will do the same regardless of what the quantum state has. The idea is that this is designed to model classical users interacting with quantum devices. We are classical people, as it.
So what is the output? Like, does it have some quantum output as well?
Of course, it is specified exactly like this. So whatever it is written here tells you in which cells is my quantum output. Then the quantum output will be this, but maybe there are more things. But this will not be part of the quantum output as defined in the table. So the reason we want this is specifically because of that. We want to, like, there is the concept of universal quantum Turing machine, like the David Deutsch concept. And that one, you can run superposition of programs, and the machine can be in superposition of internal states, and then you don't have a unique well, you can have it in terms of eigenvectors, but in a particular moment, you cannot say if you are in a halting state or not. You can be in a superposition of halting and not halting later, or maybe not even halting at all, right? So this is a problem for us. And we consider that problem, maybe we can find some approach to solve it, but we don't need to, because we can always model devices that we use, because we always will consider ourselves, maybe, I don't know, something changes a bit, as classical entities, right? So we as the programmers, we decide what the computer does, right? And then this models very well how we interact with quantum devices. So this is a completely deterministic machine, right? The flow of computation is entirely controlled by classical objects, right? And we will represent symbolically computation. Let's say we have this machine T, right? And it will take a classical input, quantum input. They will give me a classical output, quantum output. It will refer to the classical output by a C and a quantum output by a Q. So just don't necessarily always write this. And then we will talk about classical representations of quantum states, which I will use here this bar. So if I have some state rho, there will be some density operator, some matrix that I can write in the computational basis specifically, right? So it's well defined. That is a tuple of complex numbers, right? And that tuple of complex numbers that can be written in the classical tape is noted by a bar in tuple. This is used a lot. And similarly, I can consider this T with the tilde, which will be a classical simulation of the machine T, which is a machine that has a simulated classical quantum tape inside. So instead of having quantum states, it will work. It's like instead of having it's like an analogous. So if I have a laboratory with a quantum system and applies quantum operations, or I have my notebook in which I know this is my quantum state, so I will apply the matrix and the other matrix and look at the output.
Yeah, that's an interesting aspect. If you're only interested in, if you're not interested in the like time complexity, then it's simulate all of them. So why would I expect anything interesting?
Exactly. That's it. This is you'll see. Right? You will conclude exactly what you are telling, and then I will tell you what things are new from it. Like what's the value of the definition. It feels like okay, so this is so classical, right? So and they will even enhance this notion, what you're saying, enhance will highlight it by talking about some results. First, we'll just define what is a directly computable state. So let A be some. Let this is wrong. So we say that the quantum state is raw, is directly computable, directly dcq, like deterministic control quantum computable, whenever it can be outputted by a deterministic control quantum Turing machine, provided that the machine started the computation with no auxiliary inputs. So if there is some machine that taking nothing gives you some raw, we see that raw is directly computable. We can exactly prepare it and put it there. One of the things that we know is that we want to approximate raw. Sometimes it's difficult, right? Because these are continuous objects, but so we will define what directly computable is, and we will denote the set of directly computable state as Q. One of the important features of this set of directly computable is because we use a universal family in our case, in our definition, this set is dense in set of density of states. Right? So we can think about it some analogy that what the rational numbers are the real numbers, and then there is some relation with what directly computable states are with the set states overall.
So I guess things will change if you're given some input. Like once you have,
if you put something that is not directly computable here, you can have none directly computable. So now this set here is computably enumerable. So that means that there exists a program that upon input I will give me some state that as I run over all the i's, it will cover all the set of things, and I will call this pi. So this I will call that the canonical enumeration. So just this is a small example. I will not stay too long here. This is just one example. Somebody knows that what's the Cantor zigzag argument? Cantor zigzag argument. It's a proven technique that like I can enumerate all the states by running the machine number one step, and then the machine number one 2 steps, and then I go to the machine number 2 1 step, and then I start building this like pyramid, and eventually I will run all possible computations, and all of them. Right. So I can enumerate each of these computations with some I, and then I will eventually have all the possible outputable states here.
So the way an enumerator works, you can run the first Turing indexing of Turing machines, and you can run the first machine for 1 step, and the first one gets models, then the steps. Then basically,
all of these machines help because you are fixing the end, right? So yeah. So this is an example that I'm on. An important thing that you can repeat. Like sometimes you will each I is not necessarily for the different standard. And I will define computable states. So this is analogous to the computable numbers, right? A quantum state raw is computable, dcq-computable, if there is some machine that on input k classical and no quantum output gives me some sigma k, and this sigma k's they converge to my state raw in some rate, similar to how but now here I'm using the train system instead of just the. Okay. So yeah, so the notion is very analogous. Let's clear what's computable. Yeah. Now we denote this set as comp q. The other was decomp q. Now this is comp q, and now define the comp C is the set of quantum states for which the density operation, the density matrix representation in the computational base, when written, has computable complex numbers as components. So those are, you could think, the computable states, but from the classical quantum. Right? So these are the states that I can compute with my computers or with my hand, right? So are they the same? Yeah, they are. So this is basically like Ratul was commenting, right? Like it seems like this machine, what it does is very classical, and it is, right? And this is basically the theorem that tells you, yeah, indeed, this deterministic control quantum machine don't do not anything else that we cannot do simulatedly like maybe take a long time, but we don't care about time in this board, fortunately, because some of these programs are like, I mean, when you think about it, like if you will run it, it's ridiculous. Like it's so. And now we'll define algorithmic complexity, right? So let's run via quantum state and via quantum machine. Let's just call it just not to say it perfect. The algorithmic complexity of rho is given such that, and this is like it's a bit like a lot of symbols, but what it means is that the algorithmic now if I'm putting the T here, right? The algorithmic complexity of rho is the infinite of all the programs that on input the program and k approximate k to basically compute the rho. Right? So this is basically the same. So it's more like long written, but basically this is what it means is the infinite of the piece that compute. I don't know why they didn't write, but it will be easier. It's the same. And the conditional version when you give iPies. So now I'm separating the two of them just because I'm going to use a lot of this. So there's more. So now you can give some advice and it's the same. It's the shortest program that given the advice will output my targets. So this is epsilon. I never said. Sorry, epsilon is the no quantum. So when you put the input specification, you put 0. Yeah. So you're